Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Welcome. Today, we delve into sparse autoencoders and their role in interpreting complex features in large language models. They help us understand model behavior, manipulate features, and uncover semantic relationships. By enhancing model performance, they contribute to advancements in AI development, ethics, product innovation, and education. How do sparse autoencoders differ from traditional autoencoders in terms of extracting meaningful residues from complex neural networks like large language models?
Sparse autoencoders are like a special pair of glasses that help us see things more clearly in a messy room. Traditional autoencoders are a bit like a regular camera that takes a photo of everything in the room, but the image can be blurry and filled with clutter. They focus on compressing all the information and then trying to reconstruct it, which often makes it hard to pick out specific details. In contrast, sparse autoencoders act like those special glasses that help you focus on just a few important items rather than the whole room at once. They are designed to isolate and emphasize individual features or concepts. By encouraging sparsity, which means only a few neurons or parts of the model are active at any time, they allow each neuron to learn to represent a single feature, like a single color or a specific shape. This separation of features makes it much easier to understand what is happening inside complex neural networks like large language models. With sparse autoencoders, we can see which specific concepts are being activated, making it simpler to interpret and analyze the model's behavior.
Could you elaborate on the concept of monosemantic features identified through sparse autoencoders, and how these features can be manipulated to modify the behavior of large language models?
Monosemantic features identified through sparse autoencoders are like having a special key that opens only one specific door in a big house. Each monosemantic neuron corresponds to one clear concept, so when you activate that neuron, it only brings to mind that particular idea. For example, if you have a neuron that represents cat, activating it will only focus on that idea without mixing it up with others. This is different from polysemantic neurons, which are like having a key that opens several doors at once. A polysemantic neuron might activate for many concepts, like both cat and house, making it harder to understand what the model is thinking at any given time. Because monosemantic neurons represent single, clear concepts, they can be easily manipulated to change the behavior of large language models, LLMs. If you want the model to respond differently based on a specific concept, you can activate or deactivate the corresponding monosemantic neuron. For instance, by turning on the neuron for cat, you might get a response that focuses on cats alone, while turning it off could lead to more general responses. This ability to tweak individual neurons allows for greater control over how LLMs generate text, making it easier to adjust their responses and mitigate issues like biases or unwanted behaviors.
What are some of the challenges researchers face when evaluating the effectiveness of sparse autoencoders in interpreting the features of large language models, particularly in the absence of a gold standard dictionary?
Researchers face several challenges when evaluating the effectiveness of sparse autoencoders in interpreting features of large language models, particularly due to the absence of a gold standard dictionary. One main challenge is that without a definitive reference point or set of known features, it becomes difficult to assess whether the residues learned by the sparse autoencoders are accurate or meaningful. This situation is akin to trying to understand a new language without a dictionary. Without established definitions, each researcher may interpret the features differently. This subjectivity means that the quality of the learned features can vary greatly among different researchers, making it hard to reach a consensus on their effectiveness. Additionally, when training a sparse autoencoder on complex models, there can be millions of features and activations to explain. Generating explanations for such a vast amount of data is a monumental task, making it further complicated to identify which features are truly important or relevant. overall. The lack of a benchmark for comparison complicates the evaluation process, and researchers need to find better methods to determine the quality and meaning of the features learned by sparse autoencoders.
Can you discuss the innovative approaches being explored by researchers to create synthetic datasets or utilize large language models themselves to interpret the features learned by sparse autoencoders?
Researchers are exploring innovative approaches to create synthetic datasets and utilize large language models, LLMs, themselves to gain insights into the features learned by sparse autoencoders. One method involves generating synthetic datasets that can mimic the characteristics of real-world data. This synthetic data serves as a controlled environment where researchers can better understand how sparse autoencoders work and what features they identify. By designing specific scenarios, researchers can examine how different features respond and improve the interpretability of the model. Additionally, some researchers are looking into leveraging the capabilities of LLMs themselves to interpret the features learned by sparse autoencoders. This approach is akin to asking an expert in a field for their opinion. The LLM can help generate explanations or identify connections between the features and real-world concepts, making the understanding of these features more straightforward. Concepts, making the understanding of these features more straightforward. Another exciting development is the introduction of sparse crosscoders, which expand the functionality of sparse autoencoders. These new models can learn features across multiple layers, enabling them to monitor changes and streamline processes during fine-tuning. This allows for a more comprehensive understanding of how different layers in a model contribute to the overall behavior. Overall, these innovative approaches aim to bridge the gap in interpreting complex features within large language models and enhance our understanding of their inner workings.
Could you explain how the study of sparse autoencoder geometry has contributed to uncovering atomic structures that reflect semantic relationships between concepts in large language models?
The study of sparse autoencoder geometry has significantly contributed to uncovering atomic structures that reflect the semantic relationships between concepts in large language models, LLMs. This process is similar to mapping out a neighborhood to see how different houses, or concepts, are related to each other. Researchers have found that by examining the geometric structure of features extracted from LLMs, they can identify patterns that illustrate how concepts are interconnected. For example, a classic illustration of this relationship is the analogy man, woman, king, queen, which can be depicted as a geometric shape, like a parallelogram. This shape helps to visualize how these words relate to each other in a specific way. Sparse autoencoders enable the rest-study of features that correspond to single words, mainly in the early layers of the LLM data. By using techniques that reduce dimensions, researchers can create clusters that group features based on similar meanings or functions. This clustering process is akin to gathering all the houses of similar styles into one neighborhood block. Additionally, the middle layers of the model serve as a kind of filter or bottleneck, compressing the information from simple concepts into more complex and abstract ideas. This transition helps create an efficient rest study of higher-level abstractions, showing how basic words evolve into more intricate meanings as they pass through the layers of the model. In summary, studying the geometry of sparse autoencoders reveals an organized structure of semantic relationships, providing insights into how LLMs understand and represent concepts.
What are broader implications of using sparse autoencoders for interpreting large language models, particularly in terms of improving model performance and addressing issues like bias or unintended behaviors?
The use of sparse autoencoders, SEs, for interpreting large language models, LLMs, has several broader implications, particularly in enhancing model performance and addressing issues like bias or unintended behaviors. One significant advantage of SAs is their ability to facilitate feature steering. This means that researchers can selectively activate or deactivate specific features within the model. By doing so, they can guide the model's responses without negatively impacting its overall performance. This selective control allows for the fine-tuning of model behavior, enabling it to be more aligned with desired outcomes while minimizing adverse effects on its capabilities. Additionally, assays can help identify and mitigate biases present in the model. By understanding the features that contribute to biased outputs, researchers can adjust or remove these features, leading to more equitable and fair responses from the model. This proactive approach can significantly reduce the risks of unintended behaviors that may arise from biased training data or model architectures. Furthermore, the insights gained from using assays extend beyond just LLMs. They can also be applied to other types of models, such as convolutional networks. This versatility opens up new avenues for improving the interpretability and efficiency of various AI systems. Overall, the application of sparse autoencoders in interpreting LLMs not only helps enhance their performance, but also plays a crucial role in addressing ethical concerns related to bias and unintended behaviors, making AI technologies more transparent and responsible.
How do the findings from using sparse autoencoders in LLM interpretation influence future research directions in the field of artificial intelligence and machine learning?
Findings from using sparse autoencoders, SEs, in the interpretation of large language models, LLMs, are likely to influence future research directions in artificial intelligence and machine learning in several important ways. Firstly, the emphasis on interpretability and understanding of model features is expected to drive researchers to develop more refined and advanced techniques for feature extraction and analysis. While else, as researchers achieve better clarity on how LLMs process information and the relationships between concepts, it may lead to the creation of new tools and methods that prioritize transparency in AI systems. Secondly, the success of assays in steering model behavior without compromising performance suggests a pathway for more ethical AI development. Future research may focus on integrating these techniques to reduce bias and mitigate unintended behaviors in LLMs, leading to systems that are more socially responsible and aligned with human value. Moreover, the insights gained from sparse autoencoder geometry and the relationships between concepts can inspire new models that incorporate these principles. Researchers may explore novel architectures that leverage the advantages of sparse residues, potentially leading to more efficient and effective models. Finally, the collaborative approach of using LLMs to generate insights about their own features could pave the way for self-improving AI systems. This direction could lead to advancements where models continually refine their understanding and performance based on feedback from their own interpretative analyses. In summary, the findings from sparse autoencoders will likely shape the future of AI research by emphasizing interpretability, ethical considerations, innovative architectures, and self-improving systems, ultimately pushing the field toward more transparent and responsible AI technologies.
What are some potential practical applications of the insights gained from sparse autoencoders in the context of real-world scenarios involving large language models?
The insights gained from using sparse autoencoders, SAEs, in the context of large language models, LLMs, can be applied in various practical scenarios, enhancing their utility in the real world. Here are some potential applications. 1. Bias mitigation. By understanding the features that contribute to biased outputs, researchers can use sparse autoencoders to adjust or remove these features from the model. This application is particularly relevant in sensitive areas like hiring processes, law enforcement, and healthcare, where fairness and impartiality are paramount. 2. Feature steering. The ability to steer model behavior through feature manipulation allows developers to fine-tune LLM responses for specific applications, such as customer service or content generation. This means models can be tailored to align with the desired tone or style, improving user experience. 3. Enhanced interpretability. The clarity that sparse autoencoders provide about how LLMs operate can be invaluable for developers and researchers. This understanding can help in debugging and refining models, ensuring they function correctly and efficiently in real-world applications. Or goal. Cross-disciplinary applications, beyond language models. SAEs can also be applied in domains like bioinformatics, such as using protein language models, like AlphaFold, that learn the structures of proteins. This application can help scientists understand complex biological processes and develop new treatments. 5. Improving model performance. Insights from sparse autoencoders can lead to the development of new model architectures or training techniques that enhance performance on specific tasks, such as translation, summarization, or question answering. 6. Research and development of AI ethics. The findings on model interpretability and feature relationships can inform policies and frameworks for responsible AI usage, guiding research in AI ethics and governance. By leveraging these insights, researchers and practitioners can create more effective, fair, and interpretable AI systems that address real-world challenges across various domains.
How do sparse autoencoders contribute to the understanding of semantic relations in large datasets? And what impact does this have on the development of more effective machine learning models?
Sparse autoencoders, SAEs, significantly contribute to understanding semantic relations in large datasets by simplifying complex features into more interpretable components. This simplification allows researchers to disentangle features, making it easier to see how different concepts are related to one another. In a typical machine learning model, features can overlap and influence each other, making it challenging to interpret their meanings. SAEs address this by focusing on a smaller set of neurons that represent distinct concepts, leading to a clearer understanding of how these concepts interact. For example, by analyzing the relationships among features represented by SAEs, researchers can uncover patterns that illustrate semantic links between words or ideas, much like finding connections between different neighborhoods in a city. This enhanced understanding of semantic relations has a profound impact on the development of more effective machine learning models. When researchers can clearly identify and interpret the relationships between features, they can design models that better capture these nuances. This leads to improvements in various applications such as natural language processing, recommendation systems, and computer vision, allowing these models to make more accurate predictions and provide more relevant results. Moreover, by using these insights to refine model architectures or training processes, machine learning systems can be tailored to operate more efficiently and effectively, ultimately resulting in better performance in real-world scenarios. In summary, the use of sparse autoencoders plays a crucial role in revealing semantic structures within large datasets, paving the way for the creation of more advanced and capable machine learning models.
What future developments or advancements in technology or methodology might enhance the effectiveness of sparse autoencoders for interpreting large language models?
Future developments and advancements that might enhance the effectiveness of sparse autoencoders (SEs) for interpreting large language models (LLMs) include several promising areas. 1. Improved evaluation metrics. Developing standardized evaluation metrics for assessing the quality of features learned by sparse autoencoders could provide a more objective basis for interpretation. This would help researchers compare results across different implementations and applications more effectively. 2. 1. Integration with other models. As seen with the introduction of sparse crosscoders, combining sparse autoencoders with other model architectures could enhance their capabilities. This integration could allow SAEs to learn features across multiple layers, leading to deeper insights into how different parts of a model contribute to its overall behavior. 3. Advanced dimensionality reduction techniques. Innovations in dimensionality reduction methods could further improve the ability of SAEs to simplify complex data while preserving important semantic information. This would make it easier to interpret large datasets and understand the relationships between concepts. 4. Hybrid approaches, combining SAEs with other interpretability techniques, such as attention mechanisms or gradient-based methods. could provide a more comprehensive view of how LLMs operate. This hybrid approach would allow researchers to cross-validate findings and gain more nuanced insights. 5. Greater computational efficiency. Enhancements in computational resources and algorithms can lead to faster training and inference times for sparse autoencoders. This efficiency would enable the analysis of larger datasets and more complex models, broadening the scope of their applicability. 6. Interactive visualization tools. Developing sophisticated visualization tools to represent the relationships between features learned by essays can help researchers and practitioners better understand the internal workings of LMS. These tools could facilitate exploration and interpretation of complex data structures. 7. Real-time monitoring and feedback. Implementing systems that allow for real-time monitoring of model behavior and feature interactions could lead to more dynamic and responsive model adjustments. This capability could be crucial in applications where timely responses are essential, such as in healthcare or financial systems. By pursuing these advancements, researchers can enhance the effectiveness of sparse autoencoders, making them even more valuable for interpreting large language models and improving overall AI systems.
How can the insights gained from sparse autoencoders influence the design of user-centric applications that leverage large language models, particularly in enhancing user interaction and experience?
The insights gained from sparse autoencoders, SEs, can significantly influence the design of user-centric applications that leverage large language models by enhancing user interaction and experience in several key ways. 1. Personalized interactions. By understanding the semantic relationships and features that drive user preferences and behaviors, applications can tailor responses to individual users. This could lead to more relevant content suggestions. Personalized recommendations, or customized conversational styles, making interactions feel more intuitive and engaging. 2.1b. Improved clarity in communication. The ability of essays to simplify complex information can help in designing applications that communicate more clearly with users. For instance, when explaining concepts, applications can use insights from essays to present information in a way that aligns with how users understand related ideas, enhancing comprehension and reducing confusion. 3. Enhanced feature steering. With the ability to manipulate features effectively, developers can design applications that dynamically adjust to user input or context. For example, if a user indicates a preference for a certain topic or tone, the application can steer its responses accordingly, creating a more fluid and user-friendly experience. 4. Bias mitigation. Insights gained from analyzing the features learned by sparse autoencoders can help identify and address biases within LMS. This can lead to applications that provide fairer and more balanced responses, increasing user trust and satisfaction. 5. Interactive feedback loops. The understanding of how different features interact can support the creation of applications that learn from user interactions in real time. This can enable systems to refine their responses and improve over time based on user feedback, resulting in a more adaptive and responsive user experience. 6. Visualization of responses. Incorporating interactive visualization tools that leverage insights from SEs can enhance user understanding of complex responses. For example, an application might use visual aids to represent relationships between concepts, helping users grasp intricate ideas quickly. 7. Cross-disciplinary applications. The versatility of sparse autoencoders allows for their application in various fields, such as healthcare or education, where user-centric design is crucial. Insights from essays can help create applications that address specific user needs in these domains, offering tailored information or guidance. In summary, The application of insights from sparse autoencoders can lead to the development of more personalized, clear, and fair user-centric applications, ultimately enhancing the interaction and experience users have with large language models.
What are some ethical considerations that arise from the use of sparse autoencoders in the interpretation of large language models, especially regarding user privacy and data handling?
The use of sparse autoencoders, SEs, in the interpretation of large language models, LLMs, raises several ethical considerations, particularly regarding user privacy and data handling. Here are some key points to consider. 1. Data privacy. Since SEs often require large datasets for training and interpretation, there is a risk of exposing sensitive user information. If personal data is included in these datasets, it must be handled with strict privacy measures to prevent misuse or unauthorized access. 2. Informed consent. Users should be aware of how their data is being used, especially when it is part of a model that influences decisions or recommendations. Ensuring that users give informed consent for their data to be utilized in training or interpreting models is crucial. 3. Transparency. The inner workings of sparse autoencoders and their impact on model behavior should be transparent to users. This includes explaining how user data might influence the model's outputs, which can help build trust and understanding of the technology. 4. Bias and fairness. These can help identify and mitigate biases in LMS. However, if the underlying data used to train these models contain biases, the resultant interpretations and decisions can perpetuate or even exacerbate these biases. Ethical considerations must include the ongoing assessment of data sources and model outputs to ensure fair treatment of all users. 5. Accountability. As SEs are used to interpret models, accountability for decisions made based on these interpretations needs to be clearly defined. If a model's output leads to negative consequences for a user, there should be mechanisms to address these issues and hold relevant parties accountable. 6. Data handling practices. The methods employed to collect, store, and process user data must comply with ethical standards and regulations, such as data protection laws. Organizations should implement robust data governance practices to safeguard user information. 7. Impact on user experience. While insights from SEs can enhance user interaction, there is a risk of over-reliance on automated systems. Ensuring that technology complements human judgment rather than replacing it is an important ethical consideration. In summary, while sparse autoencoders offer valuable tools for interpreting LLMs, it is essential to address these ethical considerations thoughtfully to protect user privacy and ensure responsible data handling.
How might the advancements in sparse autoencoders and their applications in interpreting large language models influence interdisciplinary collaborations in research and industry?
Advancements in sparse autoencoders, SEs, and their applications in interpreting large language models, LLMs, are likely to foster interdisciplinary collaborations across various fields of research and industry. Here are some potential influences. 1. Cross-disciplinary research. The insights gained from SEs can bridge gaps between fields, such as natural language processing, cognitive science, and data privacy. Researchers from these disciplines may collaborate to better understand how language models process information, leading to new theories about language understanding and communication. 2. Enhanced AI development. Collaborations between academia and industry can focus on refining AI technology. For example, insights from SEs can help improve model transparency and interpretability, encouraging partnerships that aim to develop more robust and user-friendly AI applications. 3. Ethics and policy making. As the use of LLMs grows, Ethical considerations surrounding AI technologies will become increasingly important. Collaborations between technologists, ethicists, and policymakers can lead to frameworks that ensure responsible AI usage, informed by the interpretative capabilities of AIs to identify and mitigate biases. 4. Product innovation. Industries leveraging AI can engage with researchers to utilize the insights from essays for creating innovative product. This could include applications in healthcare, finance, education, and more, where understanding semantic relationships can enhance product effectiveness and user experience. 5. Data science and machine learning techniques. The integration of sparse autoencoders in various machine learning models can lead to the sharing of techniques and methodologies between data scientists, machine learning engineers, and domain experts. This collaboration can drive the development of more efficient algorithms and data handling practices. 6. Training and education. As the understanding of LMS evolves, there will be opportunities for collaborative educational initiatives. Workshops, online courses, or research programs can be developed that focus on teaching best practices in using essays and understanding LMS, attracting participants from diverse backgrounds. Attracting participants from diverse backgrounds. 7. Open source contribution. The growing interest in essays might result in increased contributions to open source projects, fostering community collaboration. This can lead to shared resources, tools, and findings that benefit a wide range of stakeholders, from researchers to developers. In summary, the advancements in sparse autoencoders and their applications in interpreting LLMs are poised to catalyze interdisciplinary collaborations that enhance the development, ethical use, and understanding of AI technologies across various domains.
What specific techniques or methodologies might be developed to improve the interpretability of sparse autoencoders when applied to complex data structures in large language models?
To improve the interpretability of sparse autoencoders, SEs, when applied to complex data structures in large language models, LLMs, several specific techniques and methodologies could be developed. 1. Feature disentanglement. Developing advanced algorithms that focus on disentangling overlapping features within the data can help clarify the specific roles that individual neurons play. This could involve using additional regularization techniques to ensure that each neuron captures distinct aspects of the data, thereby improving clarity and interpretability. 2. Enhanced visualization tools. Creating interactive visualization tools that map the features learned by essays can help researchers and users better understand the relationships between features. Techniques like TSN, T-distributed stochastic neighbor embedding, or UMAP, uniform manifold approximation and projection, can be utilized to present high-dimensional feature spaces in more understandable 2- or 3-dimensional format. 3. Layer-wise feature analysis. Implementing methodologies that analyze the contributions of different layers within the SE can reveal how information is transformed as it passes through the model. This layer-wise analysis can help identify which features are most relevant at each stage of processing, providing insights into how LLMs build their understanding of language. 4. Cross-referencing with human interpretations. Incorporating qualitative analysis by comparing, say, extracted features with human interpretations can help validate the learned residues. This approach can involve user studies where participants provide feedback on the relevance and clarity of features identified by essays, leading to iterative improvements. 5. Integration of attention mechanisms. Incorporating attention mechanisms into the design of sparse autoencoders could enhance interpretability by highlighting which parts of the input data are most influential in determining the output. This integration can help clarify how different features interact and contribute to the model's decisions. Dynamic feature adjustment. Developing techniques for dynamically adjusting features based on user interaction or contextual changes can improve interpretability and responsiveness. This could include allowing users to modify specific features and observe how these changes impact model outputs, leading to a more interactive understanding of the model behavior. 7. Automated reporting tools. Creating tools that automatically generate studies summarizing the meanings and implications of the features learned by sparse autoencoders can facilitate understanding. These studies could include insights into how features relate to specific tasks or domains, making the information more accessible. By employing these methodologies, researchers can enhance the interpretability of sparse autoencoders, making them more effective at elucidating the workings of large language models and enabling broader applications across various fields.
Thank you for joining us today. We've explored the fascinating world of sparse autoencoders and their transformative impact on interpreting complex features in large language models. Through this discussion, we've highlighted their ability to isolate monosemantic features, allowing researchers to manipulate and modify LLM responses. We've seen how visualizing these features uncovers semantic relationships, revealing the interconnectedness of concepts. Sparse autoencoders empower us to enhance model performance through feature steering, bias mitigation, and refined architectures. They contribute to our understanding of semantic relations in vast datasets, leading to more effective machine learning models. Advancements in sparse autoencoders, including improved evaluation metrics and integration with other models, hold great promise for boosting their capabilities. These insights can drive the creation of user-centric applications that leverage LLMs, enhancing interaction and user experience. We must remember to address ethical considerations, particularly regarding data privacy, in the use of sparse autoencoders. Interdisciplinary collaborations will continue to foster advancements in AI development, ethics, product innovation, and educational initiatives. To further improve interpretability, we'll continue exploring techniques such as feature disentanglement, enhanced visualization tools, and integration with attention mechanisms. Thank you again for being part of this engaging discussion. We hope these insights inspire your future research and endeavors in the field of sparse autoencoders.